Higher derivatives. If we have y equals f of x, then we can write dy dx. We can shorthand is y dashed, or we can write f dashed x. These are all the same thing. So dy dx is f dashed x, or y dashed. Then we can differentiate again. That's called the first derivative here. Then if we differentiate that first derivative, instead of writing dy dx, notationally we just write d2y by dx squared, and that denotes the second derivative. We can use the shorthand y double dashed, or we can even write f double dashed of x. All these notations are fine, and they all denote the second derivative. Similarly, if we differentiate that again, we'll get the third derivative, which is either y3 dashes or y3, and it's either d dash 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 dx cubed, d3, but d3y dx cubed is better, equals f3 of x, and you could put dash 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 if you wanted all three, and the fourth derivative is next, and so on. You just keep differentiating iteratively. So let's have a look at some examples to see what we mean. So differentiate dy dx, cos differentiates to minus sine. Differentiate again, we write d2y by dx squared to denote the second derivative. Differentiate this, then sine differentiates to cos, so it's minus cos then, because there's a minus tag there. And then differentiate once more to get the third derivative, d3y by dx cubed, and cos goes to minus sine. Minus minus is a plus. Y equals e to the x, differentiate. E to the x differentiates to e to the x, differentiate again, it's e to the x, differentiate again. It just continues to be e to the x. Next one, log x is a standard derivative, it differentiates to 1 over x, and we can write that as x to the minus 1. So dy dx is x to the minus 1 then. Differentiate this, minus this to the minus 2. We get the second derivative, and then differentiate again, it's minus, so it's plus 2 because there's two minuses, x to the minus 1 less is 3, minus 3. So that's the third derivative, and so on. Some rules for differentiation, well, it's a linear process basically, so the differential of one function plus another is just the sum of the first differentiated plus the second differentiated. So if we have y equals this plus this, we differentiate to get dy dx. 4x cubed, just run along the row and differentiate, plus, and sine goes to cos. Here, differentiate. E to the x differentiates to e to the x. This term minus, the 2 comes down, minus 2x to the 1, which is minus 2x. Differentiate this, run along the row, differentiating term by term. Cos goes to minus sine. Log goes to 1 over x with the minus, and 3 comes down using the power rule, x to the 1 less than 3, which is 3x squared. So that's what we do there. And the constant multiple rule is a linear process, as we said, so this also confirms that, finishes this part off really. The c can come outside as just so many of this. The derivative of so many of this function is so many of the derivative of the function. So here, if you're differentiating, dy dx, 8 lots of x squared, well, it's the x squared differentiates to 2x, doesn't it? 2 comes down, x to 1 less, which is 1. And there's 8 lots of this, so we got 16. So in shorthand, what you do is the 2 comes down in effect to be with the 8 to make 16, and you just write that down straight away in practice. 100 tan x, or tan differentiates to sec squared, standard derivative, so 100 lots of this differentiates to 100 lots of what that differentiates to. Dy dx is that then. Here, the 4 lots of this goes to 4 lots of what this differentiates to, e to the x, and the sine differentiates to cos, and there's minus 6 lots of that. So I hope that's clear for the constant multiple rule as well.